Hello and welcome to the final lesson in unit number 1, kinematics, and we're actually looking at kinematics equations in this lesson and their applications. So the goal, I want you to be able to apply the kinematics equations. So those are motion equations to solve problems from real-world situations. So what you're probably going to spend the bulk of your time with today and probably another lesson on top, or another day to finish up, because there's quite a few different questions I want you to try, but it's just practicing the various equations. So rather than develop them, I'm just going to tell you what the 5 kinematics equations are. All right, so our first equation is the one I've already given you. It's d equals vt, and this is when acceleration is 0. All right, so if acceleration is 0 in the question, there is only one equation for you to pick from, and you've already done the homework questions for that. Okay, your next equation is final velocity equals your first velocity plus acceleration times time. All right, so all of these equations, you have to have all the values except for one. So in this equation here, there's 4 unknowns. You have to know at least 3 pieces of information to use the equation. Okay. The next equation, let's go with d displacement equals your initial velocity times time plus half your acceleration times time squared. Remember, these are just equations that you're going to be plugging values into and solving for an unknown. Okay. The next one is your velocity squared equals your initial velocity squared plus 2 times acceleration times your displacement. Okay. And there is your fourth equation. And your fifth and final one is another displacement one, and it's equal to 1/2, and in brackets your final velocity minus your initial velocity multiplied by delta t, or your time. So there are the 5 formulas, okay? And you'll see that there's combinations of each one, so not all the variables appear in each one. So the last one doesn't have acceleration in it, all right, but the other 3 equations do. The bottom 3 equations have displacement in them, but this one doesn't. So you have, in these equations will allow you to solve any possible question. So you'll definitely want to put this on your study sheet or cheat sheet, all right, because, oops, you need these for the next day or so. Okay, very important. And we're going to have to use these formulas again in the next unit. So it's a good idea to get comfortable with them. So now I have a series of questions to go through, examples, and it's just a matter of you going through and solving. So James, a dragster, reached a speed of 628 kilometers per hour from rest in 3.72 seconds. How far did he travel in that time? So you have to take the information out of it that's given. So he reached a top speed, so that was his final velocity, v2, of 628 kilometers per hour. And the reason I did this one is because it's important. The book will use this once in a while. We need to have this in meters per second. In order to get it into meters per second, you have to divide by 3.6. Okay? That will convert into meters per second. So if we take the 628 and divide, oops, that's not divide by 3.6, you get 174.4. So 174.4 meters per second. So that's the final velocity. We know the time, 3.72 seconds. And we want to know how far did he travel, so d is the unknown. Now when you look at these formulas on the back page, or the previous one, we see that there is at least 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Four values. Right now we only have 2 values. We have Vt and we have delta t. So we must know another piece of information. What is that other piece of information? Well, if he reached it, we have to assume that this car started from 0. So we have to infer that it started at 0 meters per second. Once we have that information, we are now looking for a formula. So this is where you pull out your formula sheet. We're looking for a formula that has D, V1, V2, and delta T in it. So when we go back, I said that only these three formulas had delta D, V2 and V1. This one doesn't have a V2, it's no good. This one does, and this one does. We don't have an acceleration though. If you look at the information given, there's no acceleration, so this one's out. So this is our only possible formula to pick. It always works this way. It's always a process of elimination. You just have to be patient and work your way through. So delta D equals 1/2 V2 minus V1 times time. If you pick the wrong formula, all that happens is you don't have enough to solve, and that tells you that you didn't pick the right one. 1/2 V2 is 174.4 minus 0 times 3.72. And now you just have to plug it into the calculator. And when I do that, I get 300. Oops. Let's see if I draw 3 properly. Oops, I didn't want that. I don't know what that is. Come on here. 324.4 meters. So therefore, he went 324.4 meters, and I would assume it's forward, even though it's not listed. Okay, so the next one. A Ferrari's moving at 20 kilometers per hour. So that's the initial velocity, V1. And again, we have to divide it by 3.6. We need it in meters per second. Okay, so I'm giving you a couple of examples. Not all the questions you're going to have to do that, but it's a good habit to get into or know how to do it. So that's about 5, let's call it 5.6 meters per second. Accelerates to 230 kilometers an hour. So that means that it's a final velocity of 230 kilometers an hour. So kind of annoying. Got to divide this one also by 3.6. So this one's making us do all the possible steps. So 230.6, 63.9 meters per second. It does it in, gives us a time, 7.5 seconds. Find the displacement. So we are looking for displacement. We're looking for D. So this one, very similar to the previous one. It has the exact same information. So it means we're using the exact same formula. I like when it works out like that. The difference this time between the two formulas, or two examples, is that V1's not 0 this time, which is not really a big deal. So V2 is 63.9 minus the 5.6. Time is 7.5. So now we just have to plug that into the calculator. And I get 218.6 meters. So therefore, he went 218.6 meters forward. Okay, so it's just kind of a bit of a jigsaw game looking for the right formula. Using the same Ferrari as the previous question, calculate the acceleration. So pulling forward our information, we had V1 at 5.6 meters per second. We had V2 63.9, and the time was 7.5. We're looking for acceleration. It's the unknown. So now we go back. We know V1, V2, so we know both velocities and time. We're looking for acceleration. So we go back to our formula sheet. So V2, V1, we're looking for acceleration. We have time. So this is actually the winner right away. This one didn't have V2 in it. This one doesn't have, we don't have a distance, or it doesn't have time in it. and this one doesn't have A in it. So you can see that there was only one possible choice there. So we'll pull that formula forward. V2 equals V1 plus AT. Substitute in what you know. 5.6 plus. Now this is where you got to use your algebra skills. Just grade 10 formulas though. We're isolating for A. So we're going to subtract 5.6 from both sides. Leaves us with 58.3. 7.5A. Isolating for A, we're going to divide both sides by 7.5. And moving it up here, our acceleration will equal, clear that, so 58.3 divided by 7.5, 7.8 meters per second squared. So therefore, the acceleration was 7.8 meters per second squared. All right, our fourth example. An airbag deploys with such explosive force it's unsafe to use for children and small adults. Calculate the acceleration of the airbag if it deploys in 30 milliseconds. Now, I'm not too keen on doing this on test. 30 milliseconds, divide that by 1,000. I'm not too concerned. You're not going to see too many conversions on tests because it's not really the focus here. It moves out at a distance of 40 centimeters. So that's 0.4 meters forward. So we want to calculate the acceleration of the airbag. And what other piece of information do we really know here? What was the initial velocity of that airbag? Before it exploded or acted, it had a velocity of 0 meters per second. It was sitting there stationary. So we have four variables here. So we need to find one that has both D, A, V, and T. So going back, these ones have D in them. These ones have A in them. And this one has T in it. So it's got to be that one right there. Okay, process of elimination. That's all there is to it. So D equals V1 T plus 1/2 A delta T squared. We know that D is 0.4. V1 is 0. That's awesome because if you multiply by 0, that whole term will disappear. 1/2. I'm looking for acceleration, and the time is 0.03 squared. What's happening to the A? It's being multiplied by 1/2 and 0.03. So the opposite would be to divide both sides by those values. 1/2, inverse operation. So then the A will be by itself. Using the calculator, we have 0.4 divided by bracket 0.5 times 0.03 squared equals 888.9. 888.9 meters per second squared. So that's very explosive. That's acceleration. That's not velocity. So that means if it was allowed to go 1 second, if the explosion lasted 1 second, the airbag would be traveling at 890 meters per second, which is roughly, it's well over 1,000 kilometers an hour. But that's why the actual airbag only lasts, that explosion only lasts 0.03, so very, very small time. But it has to get out. So if this is the person sitting in the seat here, all right, and the airbag is there, it has to get out to the face of this person before they start to move forward and smash their head on the console. So it has to get out there very, very fast, and then it compresses or deflates very slowly, relatively speaking, giving your head a softer cushion. All right. I think I've got one more example, and then you're all set to try these questions.